Hello, Year 12s. Welcome to the last part of resistance, power, and energy. So far in this topic, we have discussed circuit symbols, PD, EMF, then IV characteristics, resistance, resistivity, etc. So now we are moving to the remaining part of the topic. In one of the lessons, we learned about ohmic resistors and non-ohmic resistors. So ohmic resistors were the ones who obeyed Ohm's law. So the VI graph will be a straight line parallel to the, straight line passing through 0, 0, which means they are directly proportional. Non-ohmic resistors, their resistance will not be constant, which means their V and I is not going to be proportional. One of such device is a thermistor. So a thermistor is made from a semiconductor, and the speciality of that semiconductor is that it has a negative temperature coefficient. I have said about this in the class before. I have used the abbreviations NTC and PTC, and I told you that time we will be using NTC more. NTC was negative temperature coefficient, which means when temperature increases, the resistance decreases. Okay, so that is what happens to thermistors. If you heat them up, the resistance decreases. If you cool them down, the resistance would increase. You need to know the circuit symbol for a thermistor. You remember the Kung Fu style where we showed how to do the thermistors? And then this is how actually the thermistor looks like, but we are more interested in the circuit symbols. Now, where do we use these thermistors? What is the importance of thermistors? So we already said that thermistors are based on how the temperature varies with the resistance, isn't it? So main places where we use thermistors are thermometers, and then in our house the heaters, the thermostats that is linked to the heaters, they have thermistors in it. Then so many things, our fridge, our kettle, our toaster, hair dryers, everything has thermistors in it. And you know, the cutest place where we have thermistors is the incubators for the babies. If you go to the neonatal unit and all, there the babies who have been prematurely born, they need the right amount of heat. So they are kept in incubators where these temperature sensing components called thermistors, they make sure that the temperature inside those incubators are perfect for our lovely babies. And in any time there is any difference, then it will alert the staff there. So thermistors have a wide variety of use. So next we are going to see the IV characteristics of a thermistor. We have seen a few IV characteristics before. We have seen the IV characteristics of a resistor or a metal wire. We have seen the IV characteristics of a filament lamp. We have seen the IV characteristics of a diode. Now we are going to see the IV characteristics of a thermistor. Now, when I was sharing this picture, I realized that there is something not correct in my graph. Not correct in the sense something is missing in my graph. What is it? Look properly. It is something I tell you off for because sometimes you also miss it. A graph should always have labels, isn't it? My y-axis has a label, but my x-axis doesn't have a label. So that is wrong. And other than the labels, the y-axis and x-axis is not having any units. And drawing graphs without units, where they have proper units, is a crime. Okay, so this is how the IV characteristics of a thermistor looks like. Now, if you look at this, and if you think about the other three IV characteristics you have drawn, this looks like a sort of a mirror image of the filament bulb. Here what is happening? Initially the current is increasing very slowly and then there is a sudden increase in current. What happens in the case of a filament lamp? Initially there is a sudden increase and then that increase starts to decrease, isn't it? So that is what happens in a filament lamp. Now, so I'm going to take that filament lamp off so that I don't confuse you anymore. Okay. So if you look at this one, the first thing that it will tell us is V and I are not directly proportional. So this is non-ohmic. The graph is not a straight line passing through 0, 0. Now what do you think has happened here? So when the voltage increased, as you can see here, when the voltage increased, current started to flow through the thermistor. That has heated up the thermistor. And when the thermistor's temperature increased, sorry, when the thermistor's temperature increased, that has caused the number of charge carriers to increase. And more the charge carriers, that means less resistance. Now there are more electrons to carry the current. So there would be less resistance. So this is what happens in a thermistor. As current increases, the temperature of the thermistor increases, and this increase in temperature leads to an increase in the number density of electrons, which then decreases the resistance. So when the resistance decreases, how do we know that the resistance has decreased? That is shown by this last part of the graph where there is a sudden increase in the current. Okay, so this is the IV characteristics of a thermistor. So in the previous slide we said as temperature increases, the resistance is going to decrease. So what is a simple experiment that we can do to study this particular behavior? So to study this, we need to show that when temperature changes, the resistance changes for a thermistor. So obviously, what are the things we need? We need a thermistor. And then when temperature changes, so we are going to change the temperature of the thermistor. What is the easiest way to do it? The easiest way actually to do is to heat the thermistor. But then that is not going to be a sensible thing to do, to directly heat the thermistor. So instead of that, what we can do is we can put the thermistor in water and you can change the temperature of water. So in that manner, we are going to change the temperature of water. And then what can we do? We are trying to show how temperature affects the resistance, isn't it? So we need to measure the resistance. For that, either you can have a voltmeter or ammeter connected to voltmeter connected in parallel and ammeter connected in series to the thermistor, or the easiest way is just to connect a ohm meter. So what you see here is a ohm meter. So what are we going to do here? Initially, we have water at a particular temperature and the thermistor is in the water. Using the thermometer, we will note the temperature of the water. Using the ohm meter, we will see what is the resistance. We will make a note of it. Then we will heat the water and for a particular temperature, note what the ohm meter says. Like that, 7, 8 different values of temperature, and for each temperature, we will measure the corresponding resistance using the ohm meter and we will plot a graph. So this will be how the graph looks like. Ignore the numbers or the scale along the x-axis and y-axis. What is important is the shape of the graph. Now, what does the shape of the graph tell you? Initially, when the temperature increases, the resistance decreases by a large factor. But the rate of decrease in resistance decreases with increase in temperature. Or initially, there is a large decrease in resistance, but later on, the decrease in resistance becomes quite gradual. So this is the simplest way of studying the behavior of thermistors with respect to temperature. Okay. So now that we have done thermistors, I'm moving on to light-dependent resistors. The answer is there in the name itself, light-dependent resistors. So its resistance depends on light. So these are also made from semiconductors, and as I just said, the number density of charge carriers or the number density of electrons in it depends on the intensity of the light falling on it. If it is too dark, then the number of charge carriers is very less, and because of that it has very high resistance. But when light intensity falls on it, or the intensity of the light falling on it increases, the number density of free electrons will increase, because of which then the resistance would decrease. So here also you need to know the circuit symbol. This is how you draw as a LDR, but this is how the LDR looks like. Okay. And just like we saw how the resistance varies with temperature for LDRs, we can have a very simple experiment to see how the resistance varies with light intensity for an LDR. So what you can see here is this is the LDR, which is connected to an ohm meter here, and then you have a bulb here. So when you're keeping the bulb closest to the LDR, you will have maximum light intensity falling on the LDR, and you can note the resistance in the ohm meter. Then move the bulb further away from the LDR for maybe 5 or 6 different, usually 7 different distances of the bulb. Each time you will see what the ohm meter shows as a resistance, and if you plot the graph, you can see that it is a very similar graph to thermistor. So here also you can see initially as light intensity increases, there is a large decrease in resistance, but thereafter for increase in light intensity, the resistance decreases quite gradually. So now that we have done thermistors and LDRs, we are moving to electrical energy and power. We did bits and pieces of electrical energy before, so some part of this will be a recap. So if they ask you to define power, the rate of energy transfer is what you call power. And this terminology is quite important. Sometimes in the mathematical questions, they will just say calculate the rate of energy or calculate the energy transferred per second. Then you should realize whenever they say the rate of energy transfer or the energy transferred per second, the rate of work done, when they're using the connecting rate and energy or energy and time, what they are asking you to do, find out or figure out is electrical power or just power. So power equals V times I. We have done that before. The unit of power, the SI unit of power is watts. So watts is V times I. Now, is watts a base unit? No. So since watts is not a base unit, what are you going to do next, or what are you supposed to do next? You're supposed to figure it out in base units. I'm not sure if we have done this before. Maybe we have done this before in one of the lessons. So if you have done it before, you can try doing it once again. No problem. If you have not done it before, do it for the first time and see. So not now, towards the end of the lesson, when I have given you space to do questions, make sure you figure out what is the base unit of power. So yes, base units of power, or what is watts in SI base units. Now, P equals VI, but from Ohm's law, we know that V is equal to IR, isn't it? So for the V here, if I substitute IR, then the equation changes to P equals IR times I, which becomes I square R. So this is one equation for power. This is the second equation for power. And again, from Ohm's law, we also know that I is equal to V over R. So if in the same first equation, if I substitute for I, P equals V times, instead of I am writing V over R. So V times V, V square. So power is equal to V square over R, and that is our third equation. So we saw that P is equal to VI, or we just stated P is equal to VI. Now we are going to derive how can we reach P equals VI. So for that, we go back to the first equation of power, which says power is equal to work done over time. And when we did the potential difference, we said potential difference is the work done per unit charge, and we said that V equals W over Q. So from that, we can say that W equals V times Q. So if I put that here, the value of W in the equation for power, then I will get power equals VQ divided by T. Now what is this VQ divided by, what is this Q divided by T? Q over T is the current. So finally we have P equals V times I. Okay, and this, you need to know this derivation. Huh? So, and it's a very easy derivation. There's no rocket science behind it. Now, so just now we saw three equations for power, isn't it? And in terms of voltage, current, and resistance, we saw three equations for power. Power equals V square over R, power equals I square RT, and power equals VI. But initially, for all these things, our starting point was power equals energy divided by time. So energy is equal to power times time. But then power has three equations. So energy transferred will also have three equations. V times I times T, I square RT, and V square over R times T. So just like there are three equations for power, there are three equations for energy transferred also. The energy transferred that we are talking here is in joules. Now, slowly moving towards the end of the topic, paying for electricity. Again, this is something you have done in your GCSEs. So when we pay for the electricity consumed by any electrical appliance at in our home, it depends basically on two factors: how powerful the device is, or the power of the device, and for how long are you using it. So combining these two, energy, again we go to our good old equation for energy. Energy equals power times time. Now, when we talk about energy consumed by the electrical appliances, our unit for energy is not joules anymore. It is called kilowatt hour. When we talk about joules, and when we talk about power equals energy times time, and when we talk about watts, our unit for energy is joules and our unit for time is seconds. But when we come to kilowatt hour, it's slightly different. It is the energy transferred by a device with a power of 1 kilowatt for a time of 1 hour. Keep this definition in mind, they can ask you. So kilowatt hour is a special unit for energy. We use that only when we are talking about the energy consumed by electrical appliances, and it is defined as the energy transferred by a device which has a power of 1 kilowatt for a time of 1 hour. So 1 kilowatt hour is also known as 1 unit. When we come to paying for electricity, that time you might see the term unit there instead of kilowatt hour. So kilowatt hour is a unit of energy. We said the other common unit of energy is joules. So how is kilowatt hour and joules related to each other? 1 kilowatt hour is equal to 3.6 megajoules. We can prove that. So 1 kilowatt hour means power is in kilowatt and time is in hour, right? But when we talk about joules, power has to be in watts. So 1 kilowatt is how many watts? 1000 watts. And when we talk about joules, hour has to be in seconds. So it is 3600 seconds. So 1000 times 3600. So 3600 and another 3 zeros, which makes it 3.6 times 10 to the power 7 joules, or 3.6 megajoules. Now this derivation also they can ask you to figure it out. Show that 1 kilowatt hour is equal to 3.6 megajoules. So I hope you got the idea behind it. Kilowatt hour is the unit of energy when we take power in kilowatts and time in hours. Joules is the unit of energy when power is in watts and time is in seconds. So we have linked them together. So 1 kilowatt hour is 1 kilowatt times 1 hour. We converted kilowatts into watts. We converted hour into seconds, and we end up having 1 kilowatt hour equals 3.6 megajoules. I hope that is clear to all of you. And the last part we have is, how do we find the cost of the electrical energy? How do we pay for the electrical energy we have used? So to find the cost of electrical energy, every energy provider will be having a rate, a tariff. So according to their tariff, 1 unit of electricity or 1 kilowatt hour of electricity will be somewhere between 6p and 15p on an average. So if you know how much electricity you have consumed or how much kilowatt hour of energy you have consumed, then you can multiply that by the cost of 1 unit to get the total cost. Now, this is something you have done in your GCSEs already. There's nothing new here. So with that, we come to the end of energy, power, and resistance. So now what I want you to do is, first, if in the previous lessons we have not written watts in base units, I think we have not written the previous lesson, if my memory is correct. In the previous lessons, we wrote resistance, the unit of resistance and unit of resistivity in base units. So here, write down watts in base units. Once you have written down watts in base units in your Carbodal textbook, page 164, question 2.2, question 5, which is on based on the power topic. And again, once you have done that, page 166, question 6. Okay, so even though I have not written it here, make sure your first question is to work out watts in base units. Then you move on to these page numbers mentioned and do those questions. The answers are there at the back of the textbook for you to check. So with that, we come to the end of energy, power, and resistance. This is there's nothing much too complicated in this, so I hope you have understood it. In case of any doubts, the next lesson we see, you can clarify the doubts. Okay, then signing off till I see you next. Bye bye.